In our last video, we introduced the concepts sample space, outcome, and events. Since these probability building blocks are written in terms of set theory language, we also studied some basic set theory notation and set theory concepts. The basic notation we learned include belongs to, and the opposite of that, not belongs to. So an element or outcome little s can belong to the sample space. It could also belong to an event A, or it might not belong to the event A. The second set theory notation is subsets. An event A is a subset of the sample space, and an event A could also be a subset of another event B. The set operation concepts we learned include union. The union of two events is also an event, and it is the collection of the outcomes such that either event A happens or event B happens. So A union B is the set of S in the sample space such that little s is in A or little s is in B. The second set of operation is intersection. The intersection of events A and B is the collection of outcomes that are both in A and in B. And the third operation is complement. The complement of an event A is the collection of outcomes in the parameter space, but that are not in A. We also discussed two basic set relationships. First one is disjointness. A pair of sets A and B are disjoint if the intersection of A and B is the empty set. Disjointness can also be defined for more than two events. A group of events A1, A2 to AN are disjoint if they are pairwise disjoint. The second set relationship concept is exhaustiveness. A group of events are exhaustive of the sample space if the union of all of these events equals the sample space. That is, this group of events exhausts all possibilities in the sample space S. You could also have a group of events that are exhaustive of another event, say B. A group of events are exhaustive of B if the union of that group equals B. The last concept we studied was partition. a group of events A1, A2, AN form a partition of S if they are disjoint and exhaustive of S. You could also define a partition of an event B. A group of events form a partition of an event B if they are disjoint and exhaustive of B. Now we are ready to define the concept probability measure. What is a probability measure? A probability measure is a function that is typically denoted by P. It assigns values to events. And the values it assigns to events are required to satisfy the 3 axioms of probability. The 3 axioms of probability are some intuitive requirements that we all can agree that probability models should satisfy. These 3 axioms include, for example, the very basic one, positivity. Probability should not be negative, should be non-negative for any events that the probability measure assigns value to. This is a very intuitive requirement because a negative probability does not make much sense to most people. The second axiom of probability is PS must equal to 1. The probability assigned to the sample space must be 1. Well, this is quite intuitive too, because the sample space by definition should exhaust all the possibilities, all the possible outcomes. If the probability assigned to the sample space is not 1, then maybe that means the sample space is ill-defined, is not including all possibilities. And the third axiom of probability, how we formulate it depends on how many elements there are in the sample space. Now, we focus on the case where the sample space has only finite number of values. So we write down this axiom in the case of finite sample space. In this finite sample space case, the third axiom is additivity. What does it mean? It means for any pair of events, A and B, such that A and B are disjoint, we have probability of A union B equals probability of A plus probability of B. That's the probability measure is additive. If we add up or union up two disjoint events A and B, the probability of the union should be the addition of the probability measure for A and the probability measure for B. That's, again, another very intuitive requirement for probabilities. To give you a very simple example of a probability measure, consider the experiment where you roll a fair die. Remember that the fair die has 6 faces. On each face, there is a number. So the sample space is the set of the 6 numbers, 1, 2, 3, 4, 5, and 6. And because this is a fair die, it's reasonable to assign equal probability for all 6 outcomes. So P1, P2, P3, P4, P5, P6 should all be the same. And by the axiom number 2, they also should add up to 1. Therefore, each of them should be 1 over 6. Now, the probability measure is completely characterized by this, and we can derive the probability of some other events from these characterizations. For example, the probability that you get an odd number from rolling a die should be equal to the probability of 1 plus probability of 3 plus probability of 5. And that should be 1/2. The 3 axioms of probabilities are very simple, but they imply a lot of consequences. These consequences are equations about probability measures that we often use later on in deriving some of the results for probability theory. The first consequence that we are going to talk about is this A. Consequence A, the probability of an empty set should be 0. Well, this is very intuitive. It could be part of the axiom, but it doesn't need to be. The 3 axioms that we talked about can already imply this one. How do we prove this using the 3 axioms? Well, you can first observe that the empty set union the parameter space equal the parameter space, because the empty set adds no element to S. Also, the empty set intersect the sample space is the empty set, which means the empty set and the sample space are disjoint. Therefore, by axiom 3, probability of the sample space equals the probability of the empty set plus the probability of S. Now you can cancel out PS on both sides of the equation, and we obtain the desired equation. P of the empty set equals 0. That's the first consequence of the 3 axioms of probability. The second consequence is also called the complement rule. So that's also the complement rule. What it says is probability of the complement of A equals 1 minus the probability of A. This is easy to prove as well. So first, we observe that A union A complement is S. So A and A complement are exhaustive of S, and they are also disjoint by definition. Given these facts, we can apply axiom 3 and find P of S equals P of A plus P of AC. And then now we use axiom number 2, which says P of S equals 1. Therefore, PA plus P of AC equals 1. And moving P of A to the other side, we get the desired equation. That's the second consequence, the complement rule. The third consequence is probability of any events should not exceed 1. This is not surprising, and it's directly implied by consequence B. And axiom 1. So why so? You can see any PA, P of any event A, equals 1 minus P of A complement. And by A1, this P of A complement should be non-negative. Therefore, that implies P of A must be less than or equal to 1. So this is by A1. The fourth consequence is also called the subset rule. It involves two sets, A and B. It says if A is a subset of B, the probability of A cannot exceed the probability of B. We can prove this by first looking at the Venn diagram. This is the Venn diagram that shows the relationship between the sets. As you can see, A is a subset of B. In the Venn diagram, it's represented by A being completely inside B. The set A, it is completely inside B. It defines a partition of B. It partitions B into two parts. One part is A itself, and the other part, this green shaded area, is the part that equals A complements intersect B. Okay. So A, as we can see from the Venn diagram, A and AC intersect B, form a partition. The union of the two sets equals B, and the two sets are disjoint. Now we can use axiom number 3 to conclude that probability of B equals probability of A plus probability of AC intersect B. Now, the probability of AC intersect B, that cannot be negative by axiom number 1. Therefore, PB cannot be less than PA. This proves the subset rule. The fifth consequence is what we call the law of total probability. It also involves two sets, A and B. It says that the set B, the probability of the set B, can be written as the sum of two probabilities. Sum of probability of A intersect B and probability of A complement intersect B. Why so? We can have a look at the Venn diagram. Let's say this green set is A, and this orange set is B. the overlapping part, the green shaded area, is A intersect B. What about this area that's in B, but not in the intersection of A and B? And that part equals the intersection of AC and B, because all the points here are in the set B, but not in the set A. So as you can see, the intersection with A partition B into two parts, two disjoint parts. So B is the union of these two disjoint parts. And these two parts, as we said, are disjoint. Therefore, by axiom 3, by A3, probability of B should equal to probability of these two parts. So that's consequence E. We will talk about something else about the law of total probability later. So that's E, and this should be F. Consequence F is the union rule. It says, it gives a formula for expressing the probability of the union of two sets. Probability of the union of A and B. In general, it doesn't equal to PA plus PB. Only when A and B are disjoint, this probability of the union equals PA plus PB. In general, it equals PA plus PB minus the probability of the intersection. Why is this true? We can first look at the Venn diagram right over here. In this Venn diagram, this orange part is B, this pink circle is A, and the intersection of A and B can partition A union B. So what's A union B? A union B is this 8-shaped area, right, formed by A and B. And this A union B is partitioned into 3 parts, this green shaded area that are in A but not in B, so that's A intersect BC. And this pink shaded area is in both A and B, so that's A intersect B. This blue shaded area is in B but not in A, so that is AC intersect B. These 3 events form a partition for A union B. Therefore, by axiom 3, P of A union B equals the sum of this partition, sum of the probability for this partition. Now, this is still not what consequence F is. So we also want to bring in A and B, the probability of A and probability of B. Now notice by the same arguments, A, the set A, is partitioned into 2 parts, the green shaded area and the pink shaded area. Right? So A is partitioned by A intersect BC and A intersect B. Therefore, PA equals P of A intersect BC plus P A intersect B. Similarly, PB equals P of AC intersect B plus P A intersect B. Using these three equations, you find that P of A union B equals P of A intersect BC, which by the second equation, it is PA minus PA intersect B. Plus PA intersect B plus PB minus PA intersect B. And if we eliminate two of the PA intersect B's, we arrive at the union rule. So this is the F's consequence F of the three axioms of probability. And this must be consequence G, the decomposition rule. The decomposition rule applies, it holds for a finite sample space, or for a finite, remember, a finite sample space is what we focus on now. For a finite sample space, any set A must contain also only finite number of elements. So it is the union of finite number of single point sets. And these single point sets are disjoint by definition because one point is different from another point. Therefore, by axiom 3, P of A equals the sum of the probability of these single point sets. And this probability of the single point sets, we just write them as P of little s, just different way to write the same thing. So these are the consequences of the three axioms of probability.